So I want to take a little bit of time today to specifically address kinematics with respect to calculus. We're going to hit this harder as we get later in the year. But for those of you that are in the AP Calc class right now and you haven't learned some of this stuff, try your best to follow along or just sort of recall what we did at the end of the year in pre-calc last year. But it's okay. Just know that eventually you will cover actually these exact problems in the AP Calc class, and you'll eventually be all caught up with everyone else in the AP Physics class. But for now, this is sort of at the end of Chapter 2 is a good place for us to pause and see what types of calculus problems we might get for this content. Anyway. So what I'd like for you guys to do is just take a moment to read the little introduction here from the Stewart Calculus book about rates of change, which applies directly to the relationship between position and velocity functions, and then unpause the video and we'll go through this first example here. So this first example says that we have somehow determined the position of the particle with respect to time, and we want to learn a lot about the system using that equation. And so we want to know the velocity at any time. We want to know the velocity at specific times. We want to figure out when the particle is at rest. We want to figure out when the particle is moving forward in the positive direction. We want to be able to kind of model what that motion looks like, find the total distance traveled by the particle in the first 5 seconds, find the acceleration, graph everything, figure out when the particle is speeding up and slowing down. So lots of questions here for us to determine. Okay, so the first thing we're going to do is to find the velocity and acceleration of the particle at any time, we need to take a derivative. So here in the calculator, you can see that for y1, I've entered the position function. And taking the derivative of this polynomial is pretty easy. We can you basically just use the exponent rule here. And we've got 3x squared minus 12x plus 9 for our y2 is our velocity. And if we take another derivative, we'll have our acceleration, that'll be 6x minus 12. So we have all of our equations. So that would answer A. And then what is the velocity after 2 seconds? What is the velocity after 4 seconds? So our velocity function is the first derivative, y2. So we'll go back to the home screen. And we can, again, enter 2 seconds. And we can enter 4 seconds. So this tells us some information here. Velocity at 2 seconds was -3. Now, did they give us any units? We know it's seconds, meters. Okay, so we've got meters per second. And then V4 is 9 meters per second. So the velocity being negative is telling us that we're heading in the negative direction. The velocity being positive is telling us we're headed in the positive direction. And again, we found this equation here was 3t squared minus 12t plus 9. When is the particle at rest? Well, it's at rest whenever the velocity is 0, so we can try to figure out when the velocity is 0. There's two ways we can do this. We can factor this, or we could use a graphing calculator. Since I've already got it graphed, we're going to go with that. Now, our velocity function was in red, and anytime our velocity function has a 0, that's where we're at rest. So that's going to happen in 2 places. Let's see if we can save some time and use the trace function. So here it looks like at 3 seconds. No, let me switch over to the red graph here, and at 1 second. So t equals 1 second, and 3 seconds we're at rest. Now it says, when is the particle moving forward? When is it moving backwards? Let's take another look at this graph. I'm going to put this in the notes here. What does it mean to be moving forward? Well, it means to have a positive velocity. So in this case, these two places where we're at rest because we're turning around. So here, our velocity was positive, so we were moving forward. And we can see that in the displacement graph because our position is increasing. Here in red, our velocity is negative, so we're moving backwards. And we can see that in the position graph here because we're returning back to the origin. And then again, moving forwards there. So they want to know the interval for which we're moving forward. That's going to be from 0 to 1, and then from 3 onwards. So we want to draw a diagram representing the motion of this particle. We usually draw the diagrams like this. Particle starts here. It starts by moving forward to some maximum value. Then it turns around and gets all the way back to where it started. And then it turns around again and goes forward. And this is t equals 1. This is t equals 3 seconds. This is t equals 0 seconds. Now, the particle moved in one dimension, but we sort of draw this snaky line because we're graphing or trying to represent the position of the particle away from the origin along a sort of loose time axis. So to find the total distance traveled by the particle during the first 5 seconds, we need to break this problem up. It would be easy to figure out the distance traveled if the particle never turned around, but it does. It reached some maximum displacement from 0 to 1, then it turned around and came back. So here it's turning around and coming back from 1 to 3. And then it moves onward from that. So what we can do is use the trace function to figure out where the particle was at each of these places. So at 1, let's switch back to the position function. The particle was at 4 meters. So this is 4 meters out. Then we go back to 0 meters. And then at 5 seconds, we're at 20 meters. 20 meters out here. So that means that the particle traveled 4 meters. Now we want distance, not displacement. So this is the scalar. So we went 4 meters plus the 4 meters back plus the 20 meters out from there. So altogether we traveled 28 meters. Now we find the acceleration with respect to time. We did that already. That was 6t minus 12. And then if we wanted to find the acceleration at a specific value, we could do y3, since I already entered the acceleration into y3. And we can find that at 4 seconds, and that comes out to 12 meters per second squared. Now we've already graphed the positions. Now here we need to be really careful with the graph to make sure we're getting all the interesting behavior here. So they told us to graph from 0 to 5. So I graphed from 0 to 5 in increments of half a second. And then just slowly expanded and contracted the vertical axis until I think I see everything that I can. We might want to spend some extra time to confirm that the position function. The blue function is not dipping below the y-axis or the x-axis there. And also we're not graphing anything in the negative time region because our system's not modeled before time t equals 0. So here's our graph. Now it says, when is the particle speeding up? When is it slowing down? So we need to ask ourselves, what does it mean to speed up? What does it mean to slow down? Well, it means that the magnitude of our velocity is increasing. Or slowing down means the magnitude of our velocity is decreasing. Remember, the red graph is velocity. So the magnitude of the velocity is initially in this region decreasing. So here we're slowing down from 0 to 1. On the interval 0 to 1. And then the magnitude of the velocity is increasing as we go from 1 to 2. You see, because we're getting larger and larger on the negative y-axis. So as we go from 1 to 2, we are, oh, sorry, no, that's magnitude's increasing, so we're speeding up there. So that's going to be speeding up 1 to 2. Now here, the magnitude along the y-axis is decreasing. We're decreasing the value along the negative y-axis. So we're slowing down again. So that was from 2 to 3. And then from 3 onwards, we're speeding up. The magnitude of the velocity there is increasing. Another thing that we could say is we're going to be speeding up when the sign of the velocity and acceleration match. So look at what was happening here. The black line is the acceleration. The acceleration is negative all the way up until 2 seconds. When the velocity is a positive sign, but the acceleration has a negative sign, we're slowing down. The acceleration is pointed in the opposite direction of the velocity. When the velocity was negative and the acceleration was also negative, that's when we were speeding up from 1 to 2 here, because the acceleration and the velocity pointed in the same direction. And then again, here, the acceleration switches signs to positive, but the velocity is negative. So those vectors are anti-parallel to each other. They're pointing in different directions. So we're starting to slow down. And then once they're both positive again, we're speeding up. All right, let's switch to the next problem. So it says a particle moves along lines so that its velocity at time t is given. Find the displacement and find the distance. Okay, so let's go back. We're going to turn these graphs off. And we'll graph that function. And this probably won't be a very good graph, but we'll try it. Yeah, we need just a little bit more room on the negative axis here. So we'll go down to -20. And they wanted a graph from 0 to 4 seconds. I'm graphing from 0 to 5. So we'll change that, or 0 to 6 actually. So I'll change that to 0 to 5. Okay. So here's the situation here. This is a velocity graph, right? This is velocity time graph because the function they gave us was velocity. If we want the displacement, remember that displacement is the area, change in displacement is the area between the graph and the x-axis. So that's going to be here and here. So we can take the integral from 0 to 6 and find the, or 0 to 4, sorry, and find the displacement. But the problem is if we want distance traveled, we need to break this up here and sum the areas separately and take their absolute value. I'm going to complete this in the notes and you guys can look at it after the video.